Welcome to this video mini lesson introduction to Pearson's R. Pearson's R is a very common type of correlation, and there are a number of different correlation procedures. But there are certain assumptions that we have to keep in mind with the Pearson's R. First of all, you have to have normally distributed data for each of the variables. The relationship between those variables must be linear in nature. You have to have randomly selected cases. Also, you have to have interval level data. Now, there are other correlational procedures that do not require interval data, but Pearson's does. Other correlation procedures can be used with ordinal or even nominal data. Also, your variables have to be independent of one another, and they have to have equal variance. Now, equal variance looks a lot different for Pearson's R than it does, for example, with Anova. And here's what it kind of looks like. So I have my predictor variable of number of hours of content coursework taken by, let's say, a math teacher, and teacher quality as an outcome variable. As you can see here, on part of my range of data, there seems to be a pretty strong correlation between my two variables. However, once I get to sort of a certain threshold here, that relationship becomes much less obvious, and there's a lot more variation with regards to my two variables here. So when you have a situation like this, that is actually what's known as heteroskedasticity, which is the idea that the variance for one portion of the range is different for that than another portion of the range. And heteroskedasticity is a violation of the equal variance assumption. Now, the opposite of heteroskedasticity is homoskedasticity, which you can see in, for example, the relationship here between number of hours of rigorous coursework in high school and college readiness. There are a couple of basic things to keep in mind with regards to Pearson's R. First of all, the R value can range from -1 to 1, -1 being the strongest and actually a perfect inverse correlation, and a +1 being a perfect positive correlation. Strength has to do with the degree to which an increase in one variable leads to a perfectly related increase in the other variable, or a perfectly inverse relationship to the other variable, whereas direction just has to do with whether it's a positive or negative correlation. So let me go back and talk very briefly about this idea of strength. From the introduction to correlation, you learned that the more tightly packed your cases are around a line of best fit, the stronger the correlation. And the less tightly packed they are, then the weaker the correlation. There are a couple of different ways to calculate Pearson's R. You can use the z-score method, which entails transforming all of your data points into z-scores. You can also do it through the computation method, which, as you can see, uses sum of squares. Both of these are extraordinarily painful to calculate by hand, so I would recommend trying to avoid that. Hypothesis testing in your Spearman's R looks like this. Your null hypothesis means that rho equals 0. In other words, there is no correlation. Your alternate hypothesis means that rho does not equal 0. So this symbol here is rho. And if you have data that supports the alternate hypothesis, what you're really saying is that your data suggests that the correlation you see in your sample holds true for the entire population. As with some of the other statistical procedures that we've talked about, we also need to look at effect size when we're talking about correlation. And effect size, as you recall, is practical significance as opposed to statistical significance. So hypothesis testing is about statistical significance. Effect size is about practical significance. And with regards to correlation, your effect size is really the explained variance, or the percent of variance in one variable that's contributed by another variable. So that's pretty similar. This idea of explained variance is what effect size is conceptually means in Anova. So that idea of explained variance is the same in effect size between ANOVA and correlation. However, this part is different. The percent of variance in one variable contributed by another variable. So there are, like with ANOVA, a whole bunch of different standards for considering what constitutes small, medium, and large effect sizes. And we're going to, for Pearson's R, just use Cohen's D. And for the effect size for correlation, small effect size would be 0.01, a medium would be 0.09, and a large would be 0.25. Now let's compare that to the effect sizes for ANOVA. If you recall, with ANOVA, 0.01 is a small effect size, so that's the same between Pearson's R and ANOVA. However, for ANOVA, the Cohen's D rule of thumb is that a medium effect size is 0.06 and a large effect size is 0.15. So in other words, large for Pearson's would be any variable that explains 25% of the variance in another variable, whereas a large effect size in ANOVA means that 15% of the variance amongst the different groups is explained by All right, so let's keep in mind here that there are some challenges with correlation. First of all, sample size dramatically affects R. So if you have a larger sample, you're much more likely to find a statistically significant relationship between your variables. Also, as we know, correlation is not causation. And we also have to be concerned about restricted range. And this is what I mean by restricted range. When you have subjects or cases that are very similar to each other, then it's very difficult to establish a significant finding. Let's say, for example, that you were looking at number of hours studied in relationship to GPA, but you were only looking at that for AP students. Well, AP students are probably fairly similar to one another with regards to both GPA and with regards to the number of hours that they study. So that would be an example of a restricted range when you have subjects or cases that are probably pretty similar. In that sort of situation, it's going to be difficult to find a statistically significant relationship between your variables. Also, with correlation, you have to be very mindful of extreme scores or outliers. They can really throw off the data. And also you have to be aware of heteroscedasticity, which, if you recall, is that violation of the equality of variance. And here's an example of heteroscedasticity where the variance differs for one part of the range as compared to another part of the range. Also, you have to be aware of curvilinear relationships, which we looked at in our last video mini lesson. And curvilinear relationships can look like, a bunch of different things, but the one common thing that curvilinear relationships all have in common is that they all involve curves. Now, there are some non-parametric correlation procedures, and we're going to learn about Spearman's row, which is one of those, in the next video mini lesson. So thank you, and if you have questions, please let me know.